Okay, the plan for this supplement is to go over two more partial fractions problems. So the first one we're going to look at is this integrating this rational expression, r of x equals 4x cubed minus 4x squared plus 8x minus 8 over x to the fourth plus 8x. So the first thing we'll do is break this into partial fractions. And we note that the denominator, x to the fourth plus 8x, it has a factor of x. And we might note that what's left over is a sum of two cubes, and we have a way to factor that. So we have x cubed plus 2 cubed. So we have an x plus 2 that factors out. And I can never remember which way the signs and all of that go in here. I know that it's going to be a quadratic because I need to multiply x plus 2 by it to make a cubic. So I need an x squared. So the x times x squared gives me x cubed. And I need a 4 with a plus. So the 2 times 4 gives me 8. And I have to figure out my cross term to make everything go away. So I have a plus 2x squared that needs to go away. So if I have a minus 2x here, that makes a minus 2x squared from the other cross term. And then the minus 2, minus 4x and the plus 4x also cancel out. So I can work out what my quadratic has to be. So the first thing I notice then is that r of x is, I'm just going to call it n of x over my denominator which is now factored. And I know from my general strategy that my linear bits get a constant in the numerator, and my quadratic bits get a linear in the numerator. So when I break this into partial fractions, I'll keep that in mind. Okay, so, and as an aside, can I factor this anymore? Just as a review, no, this is prime. We can see that by the discriminant, for instance. B squared is 4 minus 4ac, so 4 minus 16 is negative. We're going to get complex solutions to this quadratic equals 0. That indicates it can't be factored in the reals. So we're stuck with a quadratic here. So this n of x over this denominator is going to be a constant over x plus, for our next one, we have x plus 2 in the denominator. A linear in the denominator, we have a constant in the numerator. And for our third bit, we have a quadratic in the denominator. And in the numerator, we need a linear then. Cx plus d. So we want to find a, b, c, and d now. And I can say that I can multiply through by the denominator, and I can say that n of x, which I will now write out, is equal to, so if I multiply the a over x by the denominator, the x's cancel out, and I'm left with x plus 2 times x squared minus 2x plus 4. But remember, that was just x cubed plus 8. So let's write it that way. So it's a times x cubed plus 8. The b term, we divide out an x plus 2, and we get x times the quadratic. And then for the third term, we get cx plus d. And here we divide out the quadratic, so we get a factor of x and a factor of x plus 2. Okay, so think I'll make a little more room and then copy this down. So let's bring this bit down. I'm going to try to save myself the trouble of rewriting all of this, but get it into a little more manageable form. All right, so there we go. Now we have a couple of approaches here. We can see that plugging in x equals 0 is going to be nice because it'll eliminate the b and the c and d terms. So I could plug in x equals 0. On the left-hand side, that gives me -8. And on the right-hand side, the only term that's left is the a term. I have 8a, which says a is -1. I could also plug in x equals -2, eliminating the first and the last terms on the right-hand side and just keeping the b term. So what's the left side going to be? 4 times -2 cubed. So that's -8 times 4 is -32. Minus 4 times -2 squared, or -16. Plus 8 times -2, so that's going to be another -16. And then -8. That's going to be -2 cubed plus 8. First term goes away. The last term goes away. -2 plus 2 is 0. So I get b times -2 times, and what do I get when I plug -2 in here? I get 4 plus 4. And then -2 times -2 is plus 4. So I get 12. Okay, so a little arithmetic to do here. So I have -64 minus 8 is -72 equals -2 times 12b. So I can see the -2 is going to divide out and give me a 36, and the 12 is going to divide out and give me a 3. So I get b equals 3. Okay, so let's, we have a and b, we need to find c and d. Let's match up our cubic coefficients. So on the left side, we have 4. On the right side, we have ax cubed, so a, plus bx cubed from the b term, plus, we note that for cx plus d times x plus 2, the only way to get a cubic is to multiply those 3 together, so we get a cx cubed. So what does this say? 4 is -1 plus 3 plus c. So we have 5 minus 3, c equals 2. And we've got to find d. We can kind of see that, doing something like matching up the constants or something is not going to work, right? Matching up the constant is the same as plugging in x equals 0. So that's not going to work. So we need something independent, and we might as well pick something easy. Let's just go with, say, x equals 1. So maybe over here in the corner, I'll just do x equals 1. You could have chosen x equals -1 or x equals 2 or something as well, and any of that should have worked. But x equals 1 is probably the easiest one that we haven't used yet that we can plug in. So on the left-hand side, we have 4 minus 4, so that's 0, plus 8 minus 8, which is 0. On the right-hand side, I have 9a plus b times 1 times 1 plus 4 is 5, minus 2 is 3, plus, and then I have c plus d multiplied by 1 multiplied by 3. And I know that a is -1. I know that b is 3. So I have 0 equals -9 plus 9, so they go away, plus c plus d times 3. So this tells me c equals -d, or d equals -2. So there's my A, B, C, and D. I'm going to just come up here and write these in. So A was -1, B was 3, and C and D were 2 and -2. And now I want to integrate this. So if I integrate that rational expression, that's integrating this, which is just integrating all of this. So we've made it simpler. I'm still a little worried about that last term there. We might have to do a little massaging to make that work out, but we'll get to that a little bit later. But we see we can do the first two integrals pretty easily. So integral of -1 over x is just negative ln absolute x. Integral of 3 over x plus 2. And then I need to figure out the integral of this. So the first thing I might look at is something simple. You know, I don't know. I don't think I know the integral of this right away, but I can see that a u substitution is going to be promising. And nicely enough, the u substitution does work without any extra manipulation. We have du equals 2x minus 2 dx, and that's exactly what we needed. So we see that this last integral actually turns out to just be log of the absolute value, x squared minus 2x plus 4 and plus c at the end. We could combine those logs, but I think we get the point, and I will leave it there. Okay, so we're going to move on to this problem now, using partial fractions to integrate x to the 4th plus 4 over x squared plus 4. And we note that here the numerator degree is bigger than the denominator degree. So the first thing we'll have to do is some long division. We've seen a problem like this before, but there is a little detail that we're going to encounter here that we want to make sure that we don't forget about with long division. So I have x squared plus 4 divided by, x to the 4th plus 4. Divided by x squared plus 4. And one thing that can kind of come up is, what if I have a polynomial on top where I have missing terms, where I have like 0x cubed, 0x squared, and 0x. I can get easily tripped up in my long division if I don't include those. So I'm going to come down here and I'm going to be careful, and I'm going to include all of my even 0 coefficient terms. Okay, so I'm going to do this division. X squared goes into x to the 4th, x squared times this gives me x to the 4th plus 4x squared, and I have a subtraction there. I'm going to distribute that negative like I usually do, make it just a little less error prone. X to the 4th minus x to the 4th, they go away. Then I have a negative 4x squared. I don't have a 0x to bring down, so I'll bring down this 1. So do you really need, to add all of these zeros in? Probably not, but it gives you kind of a placeholder to keep things lined up. And so if you ended up with just this negative 4x squared directly under the 1, that might throw you off a little bit. If that wouldn't throw you off, you probably can get by without putting all of these zeros in. But I usually put them in as placeholders just to kind of keep things straight. So x squared goes into negative 4x squared how many times? Negative 4. So I have negative 4x squared and then minus 16 being subtracted. So again, I will change the signs on all of this. These go away and I have 17. So I see that my rational expression is x squared minus 4 plus 17 over x squared plus 4. And I just realized that I made a little mistake at the beginning when I copied everything down. So luckily it's not too bad to fix. I have an x to the 4th plus 4, and I copied it down as a plus 1. So this should actually be a 4. This should be a 4. And then 16 plus 4 is 20. And so this needs to be 20. So sorry about that. And now I want to integrate r of x dx. And this actually turns out to be pretty straightforward. So this is going to be the integral of x squared is 1/3 x cubed. The integral of negative 4 is negative 4x. And then we have this bit here, 20 over x squared plus 4. So we'll put a plus here just to remind ourselves that we're not quite done yet. So let's break this off and do this over here on the side. I can see this looks a lot like 1 over 1 plus x squared, a lot like something that's going to be an arctan. If I divide top and bottom by 4, that might help. And I can write it this way. So dividing the 20 by 4 gives me 5. Dividing the 4 by 4 gives me 1. And x squared divided by 4 turns into x over 2 all squared. So this is going to look kind of like 5 arctan of x over 2. So if I differentiate this, I get 5 over 1 plus x over 2 squared. That's what I want. Chain rule pops out an extra 1/2. So I need a times 2 to counteract that. Okay, so what's the integral? This third integral going to be? It's going to be 10 arctan x over 2 and plus c. So even though this one, looked a little scary, it looked kind of like it might be really complicated. It turned out to not be that bad because most of the rational expression just came off as a polynomial. And then we had a fairly simple rational expression left over here at the end. Okay, so like I mentioned before, I'm going to try to do more supplemental videos that are shorter in length. So I think I'm going to end this one here, and then we'll come back with the next one in a separate video.